All right, so I get started. So welcome back. This is the seventh session. We only have this one and one more to go for the whole workshop. And today we're going to cover the very exciting topic, and I know some of you are definitely looking forward to it, of the neural networks. So before all of that, as usual, just to get things going, get to your Python the repository you cloned, and just run git pull upstream master to make sure you get the latest. And I hope everyone had a chance to install the PyTorch package following the instructions. Has anyone you had issues with it? Do you have all PyTorch installed? Right? Otherwise, it would be kind of boring today. You'd just be staring at me doing PyTorch stuff, and you'd ought to be doing it yourself. All right, good. So today will be a bit different in the way I'm going to approach this because I cannot just dive in neural networks without really telling you what neural networks are. So the first half of today's session will be actually a bit of like lecture where you get to just listen to me talk about what a neural network is, how do you go about using it, what are the ideas behind these things called modules, how do you compute a gradient using something called backpropagation, and then even perform the conceptual understanding of gradient descent so you can actually be ready to use something like PyTorch to train neural networks. All right, so we just get started. We have a lot of material to cover today. I hope that we'll cover every material I planned for today. If not, then I'm just going to push it a bit into the next session, and then the next session will be a couple more topics, and then wrap up. All right, so this is a session. It's Edgar's Guide to Neural Networks. So first thing first, you have to ask the question, what is a neural network, right? So potentially you've seen diagrams like this where there seems to be a bunch of circles connected to each other. In neural networks terminologies, you tend to label these as separate layers. So if you have like green ones are x's and blue ones are y's, it still doesn't really give you an idea of what this is about. But at least in terms of labeling, what we tend to say is that these circles are the neurons in our neural network. And here in this case, you have 2 input neurons and 3 output neurons. So the input neurons are feeding into the 3 blue output neurons. Now, the term neural network obviously stems from the term neuron that we actually study here in neuroscience, right? It's more of an inspiration. It's just that looking at how neurons are connected to each other and supposedly do something very complex, such as human behavior, that this otherwise simple connections between simple-looking neurons, now you can disagree with whether a neuron itself is really simple or not, but at least otherwise simple-looking neurons getting connected to each other, really performing this very fantastic and interesting behavior inspired scientists, especially computer scientists, actually quite a few decades ago, almost near 100 years ago, to think about what if I could put together something that looks like a brain, maybe it would do something interesting. Well, so these are the inputs, and these are the outputs. And inputs and outputs are connected by connections or weights, right? So let's look at one output at a time. The way neural network computes is that an output is defined as a weighted sum of the inputs. Mathematically speaking, this means you take the x1, one of the input, multiply by one of the weights, the one that connects from that input to the target output, here in this case y1, and you basically multiply the weight onto the input, and you do the same on the other one. You multiply the weight w1, 2 onto x2, and you take the sum of it, and that's not it. You also then run it through something called an activation function. Now, activation function is just a general class of any nonlinearity function, and you have a lot of choices when it comes to what activation function to use. But one of the most popular activation function would be something called ReLU, which stands for rectified linear unit. Because mathematically speaking, this is just something that ultimately thresholds the input. So if the input to an activation function is less than 0, it flattens it to 0. And anything above 0, it keeps it the way it is. So it's a rectifier in the sense that it keeps everything positive, or ensure the output is positive. And it's linear because the portion that is not zeroed out is a straight line. So this is called a rectified linear unit and one of the more common nonlinearities. It's nonlinear because it's not just a line, right? So whenever you encounter the term nonlinear in pretty much any field from here on, all it means is that it's not a line. I mean, that's what the term nonlinear means too, right? So don't derive too much into it just because someone says, oh, this is a nonlinear computation. All that guy is really telling you is like this is not a linear function, right? And whether that means anything to you quite depends on the context. All right, so back. So basically we had activation function taking in sum of input, weighted sum of inputs into each node. And if you were to use some index notation, you can write it as such. So here I even use summation notation to succinctly write it. So when you have a case like this where a bunch of input nodes and output nodes connected to each other in the fullest form, so basically every output node actually has an input from every input node. This is called a fully connected neural network or fully connected layer. Here there's only one layer, there's only one step. And this particular one has a nonlinear activation function, which we know happens to be, say, a ReLU in this case. So here's a way to note that for one output neuron, you can say that yi is activation over sum of the weighted inputs. Or if you're more familiar with the vector and matrix notation, you can rewrite it as such. Right? It just becomes some weight matrix W multiply onto the input vector x. And that gives you the whole vector of outputs. So y1, y2, all the way to whatever, how many y you have, y equals. And here I'm also saying that y equals a activation of wx, but this could also be thought of as being a function of x and w. Right? Your output y depends on both the input x and also the weight matrix w, which is really the connection strengths. Interesting thing about the neural network then is that you can train this even one layer network like this by adjusting the weights w. And by actually adjusting this in some clever fashion, you can achieve fairly interesting input-output relationship. Right? For given input, you can make it basically spit out some interesting outputs. And you have a lot of knobs to turn. Basically, you have as many as all the connection weights w to adjust to achieve the desired output. Okay, so like I said, that's the one thing. Now, single layer is fun enough, but you can actually stack this further to get even more complex functions expressed. So here, what you have is x as an input feeding into some intermediate layer of neurons, which then further feeds into the final output layer of neurons. Whenever you have something more than just input and output layer, you call those hidden layers. And this, by definition, is what's considered deep neural network. So whenever you actually guys encounter the term deep neural network, it more or less means you have at least one hidden layer. So don't be fooled, it's not that deep. Or it may not be that deep. But here the idea is that because you stack them up, you have both the first set of connections, W1, I labeled that way, and second set of connection, W2, that you get to train or you get to adjust both of them. So you can imagine that now by having this stack up, you have even more weights to train, or weights to adjust, and as a result, you get to actually express far more complex relationship between the output y's and input x's. Together, if you were to write this as one big function, it just means that y is some function of x, the input, and then two weight matrices, W1 and W2. Okay, so the key idea when it comes to neural network is that now you have something that relates input and outputs with otherwise fairly simple connections and some activation function where the only thing you can really change is the weights. You actually might be able to get some interesting relationship, interesting functionality out of your neural network by adjusting the values of the w's. So in other words, you can create a network that does some interesting things by cleverly choosing input and output, thinking what an input means and what an output means, and then go about learning the W. So one good example would be something like image classification. In the image classification, you treat the image as the set of input neurons, if you think it that way. So for example, in the case of this, where it's 512 by 512 by 3 images, so you know this is an RGB image we talk about, it's a colored image. So I'm not going to do that math in my head, but that means if you were to treat one pixel as a neuron, this is simply 512 by 512 by 3 mini neurons as an input. Okay? And this is where you have to be a bit clever. What is it that you're trying to do and how to formulate your output? One common way to do classification. So classification idea is that you take an image and classify into one of n categories. So predetermined categories. You don't like make it randomly come up with the names. So here I came up with 5 categories into which I want my image of dog to be classified. Oh, sorry, I gave you an answer in case you didn't know this is dog. to be classified, and I'm telling it probably has to be dog, cat, monkey, mouse, or squid. Those are very equally likely on animals you encounter in the everyday world, obviously, right? So yeah, here basically, if you were to say maybe what I'm going to have is the vector of size 5 corresponding to the 5 categories, and what each of the values is going to represent is the probability that the image was that category. So here, I mean, just an example, toy example, if I were to feed an image, maybe this is an answer I get, some vector of size 5. And if you look at it, at least it classified, it thinks that 67% this is a dog. But it also thought there's like 20% chance this is a squid. So it's okay, right? It performs okay. So let's try another image. This one's harder. It thinks this is 34% dog. And it's a bit more convinced it's probably squid or monkey. So you could have situations like this, but you get the idea that input is an image. But again, because you know the fact that image could be an array is nothing but a bunch of elements. If you were to treat each of the pixel as a neuron, you again have 512 by 512 by 3 neurons, input neurons coming in. And after many layers, you can have 5 neurons as an output, where each neuron represents the probability of particular class that you want to classify into. So this is the very basic way of using neural network to perform something like image classification, one of the most popular applications of neural networks. Okay, so once you identify how you want to say what an input is and what an output is, then of course we are left with the question, okay, how am I going to actually get some interesting behavior out of your neural network? You have to adjust the W so it actually performs something interesting. In other words, how can I train my neural network? So in order for us to discuss this topic of how is it that you can train a neural network, I want to take a step above you and reintroduce you to the concept of neural network from a bit broader computational perspective. So far to you, a neural network is a bunch of neurons connected by lines, right? And you've pretty much only encountered fully connected neural networks. But there's actually a way to think of neural networks that's a bit more generic, functional graph, as we would talk about it right now. So another way to think about neural network is that it's just a connected sequences of what we call modules. So here, one of these like ellipses represents a module, and I'll soon get to what a module is, but the left side you have 3 modules connected to each other. The right side also has a total of 6 modules connected, but in a bit fancier fashion. But the common thing is they're both consisted of modules. And if you want to go into details, I'll also tell you that key is that you cannot have cycles. As in, like, there shouldn't be a path that if you follow that you can come back to the same node you started off. As long as you don't have that, you actually have a neural network. Okay, so you'd be wondering, what is a module? So module is the building block of any neural network, and all it is really is something that defines an input and an output. And basically it's a function. But the key is that it defines an input-output relationship with a potential parameter, theta in this case. I'm calling it theta, but it could have been really anything. All I'm saying is basically, as long as you have a function that takes in an input, returns an output, and it in itself has some parameter that may be adjustable, you have a module. So, more mathematically speaking, this means that if I let the x input be x, output be y, same notation we used earlier, and my function itself is f, and I use the subscript theta to denote that it has a parameter theta. That means the overall relationship is that y is a function of input and theta. This should look relatively familiar to you, because it's pretty much what you just saw in terms of the fully connected network. Fully connected layer is nothing but a module in this view. So as we saw, the fully connected layer, there are no input neurons, which could be treated as a vector of x, and output neurons y as a vector, and then weight matrix w. Overall, the function of input-output relationship is y is some function of both the input x and w, or which you could specifically write out how the exact relationship works out, but it is nothing but a function after all. So, and if the requirement for something to be a module is that it takes an input and spits out an output with some potential parameter, well, if I were to say theta is the w, you indeed have a module here. So I'm not talking suddenly of different things. The fully connected network we talk about, it was just one module. But here I'm taking a bit step back and thinking of, if I were to not be so tied down to fully connected network, fully connected layer, and think in terms of modules, actually neural network theory and discussion also completely applies and actually gives you even broader perspective on it. Okay, so when you chain together these modules, what you just do is that you start from the input and you go to one function, and the output of that function or output of the module becomes an input of yet another module. And you simply follow the process. So here, if I start with an input x, I get the intermediate output y by saying y is f of x with theta, theta being the parameter for this module. And the y then becomes an input to the module g. Right? So the z, there's a final output z here, which is nothing but g of y of phi. And here I'm kind of having a grayed out version. Basically, you can chain them together and write it as one big function, where z takes in f of x comma theta as input for g, and overall you can treat that whole thing defines yet another function, which I'm going to call h. So h has, again, input x, but because it's a chaining of the two modules, it has both the theta and phi as its parameter. So computing sequence of function as defined like this, where you just step through the arrow basically, or follow the arrows, this is called a forward pass of a neural network. And typically speaking, this is pretty cheap in the sense that it's fairly straightforward to just go ahead and compute a forward pass of neural network. So from now on, if you ever talk to a guy who supposedly trains and works with neural network and they say, oh, I'm just doing a forward pass, all he means is he's just running input through the network. Okay? I guess one thing I didn't really clarify through the whole workshop, but hopefully you're getting the idea, is that oftentimes they trick into getting to a field just knowing the lingo and start to talk like them, or at least understand the lingo. So here for neural networks, I'm going to at least tell you a couple lingos that you can get onto, and you can basically understand the fact that most of them were not saying that anything that difficult. All right. So network as a whole here, so here I'm like relabeling it. Here I'm basically saying the blue one has a parameter alpha, green the parameter beta, and the red one parameter gamma. It really doesn't matter. It just they all have some parameters. So a whole relationship between the overall input x and the final output z could be described as yet another one function, which is, again, we know is a chaining of individual modules. So I say I'm going to call this h, and I denote it saying h of x. Here I'm using semicolon to even indicate that there's an input and parameters, but in reality they are just function of input and all the parameters that were found in the chain. Okay, but this overall is still boring. If I tell you, hey, this is my neural network and I'm done, you're not going to be that interested because so far it's not doing anything interesting to you. So obviously we want to make this neural network, this chain of module, do something interesting. In other words, we want to make it approach, say, some target function. Just as I said, the overall thing implements a function h. That itself might not be that interesting. You want to make it behave like something else. Maybe you want to behave like a machine that can classify images. That's a target function, right? If you think about any classifier, it's something that takes in an input, say an image, and spits out an output, say a classification vector, just like the one example we saw. So if that's your goal, that's the target function that you wish your entire neural network to approximate or approach. So this is where training comes in. So if you're to train the network, obviously what you want to do is you want to take your h and make it approximate the target function t by adjusting all the knobs. In this case, we have alphas and betas and gammas. You find the best set of alpha, beta, gamma that makes your function, your neural network, be as close as possible to what you want it to be. This is what training is about, yes?
So does each module have one layer or an unspecified amount of layers?
Unspecified amount of layers. And we'll get back to the composition piece here. Okay, so let's just get back to this picture. So if you have an input x, and now you also have a target t. So for that particular x, say you want the output to be t, right? But so far your network output is z. You want to actually ask the question, how can I adjust all my parameters? In this case, we're back to thetas and phis. How can I adjust the parameters, say just by a bit, because I want to do a bit at a time. I don't want to commit too much. Adjust by a bit so the difference between my output and target could be smaller. Now, interesting enough, this is the same question, or effectively the same question as asking, how does a tiny change in my parameter affect my output? Because if you know the answer to this question, it shines light on how could you adjust your parameter to get a better output. Now, this is where you have to introduce a concept called cost function, or also commonly known as a loss function. A cost function effectively, so here I'm taking one example. This is a very typical and common cost function called mean squared error, or sorry, squared error at least, where you basically take the two things you want to be similar to each other. Z is the output of your network, T is your target. You take the difference and you square it. So you can see that if it's different at all, it will be some positive number because it's squared. And only time this is small, as in 0, is when it's identical to each other. So cost function really tells you how off you are from the target. And this is one example of cost function. There are many examples of cost functions, and what you use could really depend on the application. And sometimes just up to you. You come up with what makes sense as a cost function, and you try, and one could work better than another. That's actually part of the fun and a bit of nightmare of training good neural networks. So the goal here, but since it's a cost, you want to minimize the cost. No one wants to have a large cost. You're trying to minimize the cost function. I already noted the fact that this is also commonly referred to as the loss function. So one way to think about this is that we're interested to know how it is that the C, say, depends on output of each module. So at least we know how the output, how the module itself affects the cost. If you can know the relationship, maybe there's a way we can adjust the behavior of each module such that overall we get a better cost, lower cost. Right? And it turns out you can do this in steps. Like you don't have to actually try to jump to individual outputs. And this is what we actually get to do now, going backwards. So first thing first, if you ask the question, okay, like something like, oh, how is it that say my cost depends on the final output of my network Z? It turns out you can assess this by computing something called gradient, which I hope you're all familiar with. It's just basically derivative of the cost, or partial derivative of cost with respect to the output Z. This is basically a succinct summary of how is it that C depends on Z. So I'm interested in computing. Well, given the C is function defined on Z, this is actually pretty straightforward to compute. It's just straight up gradient computation. So that step is pretty straightforward. The question is now, I want to say how is the output of my earlier module, say the one F, that outputs Y, how does the Y depend on C? In other words, I want to know this gradient dc dy. Now you can think of maybe like chaining all the functions and doing a complicated gradient, but it turns out you can actually be a bit clever about something you already know to get there. So you say already know the fact that going from Y to Z, you go through function G, right? So Z is equal to G of Y comma phi. So at least you can answer the question of dz dy. How does Z relate to Y? And you can compute that just by taking the gradient. And this is where the chain rule that you use every single day of life, I'm pretty sure, comes in, where you can combine the fact that you know how C to Z relates because you have dc zz, and you know how Z to Y relates because you just computed dz dy. Well, you just multiply them together and you get dc dy, how C relates to Y. And yeah, I'm not just coming up. This is actually correct. You can do this according to chain rule. All right? All right, so good. We successfully computed the dc dy, how C relates all the way back to Y, just by couple multiplication and simple gradient computations. We can continue this step. We want to now say how C relates to X. Maybe X wasn't the input. Maybe there's even more chains continuing down. It really doesn't matter. You can ask the question, how does X relate to C? Again, not by trying to go from C to X directly, but you already know how C relates to Y. And you do know how Y relates to X because you know the function f. You can just compute the dy dx by taking gradient over f, and you multiply that onto dc dy. C to Y relationship multiplied by Y to X relationship gets you C to X relationship dc dx. Well, guess what? This is how you actually apply sequences of chain rules to get the gradient with respect to individual outputs. Now, once you know how cost relates to the output, now it's a time to ask, okay, how can I change this relationship? Namely, how is it that maybe I can adjust my parameters to make my cost different, right? And namely, I want to decrease the cost. So this is basically asking the question of how is it that now C relates to one of the parameters, say theta? Well, you already went from C to the output of the function Y. And because you know the fact that y relates to theta by the function, y is a function f of x comma theta, so you can ask the question y to theta relationship by taking partial derivative or gradient with respect to theta. So you get the dy d theta. Since you already know dc dy and dy d theta, again, it's a chain rule. You multiply them, you get dc d theta. This is an answer to the question, how does my cost relate to that particular parameter, theta? Well, if you ever heard the term backpropagation neural network, what I have just described is actually one of the fullest detailed backpropagation. There's actually not much more to it than that. Basically, it's just a sequence of gradient computation and chain rule to get from the cost to any one of the outputs and then any one of the parameters you're interested in. So just to summarize, when you have a module, you have a relationship, input-output relationship. The y, say, is equal to f of x theta with this optional parameter. I keep on saying optional because you could have a module that doesn't have an adjustable parameter. It's totally fine to have it. It becomes a block you throw in and there's nothing to be adjusted about it. It could still be pretty useful. If you want to be able to perform what's called backward pass, the back propagation, you need to be able to do gradient of the output gradient of the output with respect to the input, so you can follow it through and go on to the earlier module. And you also need to be able to go from the output to the parameter, so that's the y d theta. If you have these three things computable, that is a functional modules. And it turns out you can combine any of these modules together, and you can always follow forward pass because you can just feed forward it. But more importantly, backward pass to do the back propagation as long as these three things are true. So in fact, this actually goes back to one of the questions, is that one of these simple looking modules I presented could itself actually be a very complex module, namely consists of many other modules. But because of the fact that I can actually go input to output, right, I can feed forward it. And because as long as each of those define gradient respect to input and gradient respect to parameter, I can do back propagation to go from gradient respect to the input and also gradient respect to every one of the parameters. This as a whole is a good module. And you don't have to worry about the fact this is itself a pretty complicated thing. Okay, so far so good. I know I'm going decently fast, but hopefully this is clear. All right, so good. We have gradient, and I was somehow convincing you that knowing gradient is the key to be able to adjust the parameters. One thing I really haven't shown you is that how do I use the gradient to actually adjust the parameters. Now, you might be able to believe the fact that if I know how cost relates to parameters, it gives me some information of how to adjust a parameter. Let's now look at how you actually can adjust a parameter. Well, it turns out what you do is a procedure called gradient descent, and I'm going to try to pictorially depict this. So imagine a very simple network, right? It has some input-output, but we actually even strip that away to say, ultimately speaking, the cost I'm trying to optimize depends on, say, a parameter. And here I'm even reducing to the case of single parameter. So this might be what my cost function looks like as I change a parameter. We want to minimize the cost, right? So that means the smallest value is the optimum value of the theta, or the parameter. We want to actually get there. But because we don't know what the optimum is, at least we don't know starting what the optimum is, we usually have an initial guess for the parameter that's somewhere away from the optimum, right? It's inevitable. If you somehow already can nail it by the time you initialize it, good for you, right? I don't know how you do that, but that'll be pretty cool. Rest of us don't have that, ability to be able to tell what an optimum is, so we have to start with a random guess. Or you can have an educated guess, whatever you want, but it's more or less different from the optimum. In gradient descent, what you do is you compute the gradient. So this is the same thing as this is ultimately what the back propagation gave you, right? If you have a parameter that affects your cost, the whole exercise of back propagation was just to get you this gradient, how the cost relates to your parameter. In this case, so if you remember the fact that for 1D function like this, the gradient is nothing but a tangential slope. Here you have dc d theta, which is some positive value, that's for sure, right? It's a positive slope. What you do in a gradient descent is that you move your parameter in opposite direction of the gradient. So opposite here means that if the gradient is plus or positive, you move your parameter theta in a negative direction. So you move it kind of like that. and I adjust and I move. Guess what? I got closer to my optimum. I can do this again. Now at the new value, I recompute my gradient because it's different place. The gradient's slightly different. It's shallower now, but this is still positive. So I move further. Now notice I'm not moving as much. This is because you tend to move the amount indicated by the gradient slope. So the steeper the gradient, the more you move. The shallower the gradient, you move less. And this becomes critical because at the end of the day, if you are at the optimum, that's nearly zero, right? If you're really close to flat area, you probably don't want to move as much. You are getting pretty close. We'll actually soon talk about what happens if you actually move a lot. Okay, so I got closer. Now let's take another example. What if I started on the opposite side of the optimum? Well, I compute the gradient, and it's a negative slope. So I do the opposite, right? I now moved in positive direction, and this is pretty steep, so I moved quite a bit, and I got closer to my optimum. So this is the gradient descent. I mean, there's actually not much more to it. This is a 1D case, but when it comes to high dimensional case, with respect to each parameter, you're still actually doing the same exact procedure. So we basically adjust the parameter by taking the gradient and moving in the opposite direction of the gradient. So if the slope is positive, you move in a negative direction. Slope is negative, you move in a positive direction. And you tend to move in the proportionate amounts to the gradient slope.
What if you get stuck in a loop?
You are stuck. You are stuck. Yes. Yes, we do this over. There are many tricks to adjust the terrain. Basically, you kind of move the function itself so you have a potential of getting out outside the scope of the class, but I'll be more than happy to talk about it, maybe if I have a time at the end.
Something like the function, for example, if like this probability of
Yeah. There are many optimization techniques. So if you're interested in that classes of optimization, look at the Bayesian optimizations, and they actually have a ways of adjusting probabilities. It's also related to another optimization called simulated annealing optimization, which has this idea of temperature. Yeah, it comes actually a bit from like ideas saying things like PCR. It's pretty cute. Okay, so yeah, but key with the gradient descent is that you don't get to optimum immediately. You actually do multiple steps, right? And one thing I'm gonna now do is this idea of learning rate. Basically, how big you move is proportionate to the gradient, and also another factor, multiplier, called learning rate. So if I have a very small learning rate, what I get is something like this. Okay, I started with initial value. I have a slope, gradient again. I adjust. So nothing different, but because my learning rate is tiny, I move a tiny amount. I move. I do it again, and again I move a very small amount. Do it again, small amount. So you can see that if the learning rate is pretty small, I mean, you're still getting closer, but it takes forever, right? And given that your goal is not to just sit in front of your computer and watch your computer just take away bits and bits, like you wanted to get to the answer as quickly as possible, I mean, too small of a learning rate is not really going to do you a favor. Okay, so I know what some of you are going to say, well, just make it large. Like, why don't you just go learn it quick? Well, take the gradient, yeah? If you have a large learning rate, this is what you're going to do in terms of step. Okay, you move. All right, well, you flipped it the other side. Okay, let's continue this, right? Okay, now I take the slope. Guess what? This is even like steeper of a slope. With the huge learning rate, I'm moving like that. I'm here. So did I get any closer to my optimum? Not quite, right? Now, I'm not necessarily saying like if you make it large, it's always fail like this. That's not necessarily true, but you could imagine that it's quite possible that after you move far enough and got close enough to minimum, rather than really getting to the bottom of it, I mean, literally, you might just jump back and forth and really have a hard time converging on a solution. So that's what could really happen if you have a large learning rate. So if you have a large learning rate, you could easily overshoot your target. So this is why you don't just make it huge. You have to kind of be a bit careful about it. And this is one of those nightmares. I have a lot of nightmares about neural networks, but one of the nightmares is this learning rate. Like, what do you make your learning rate? I wish there was an easy answer I could tell you, like a recipe of how to choose learning rate. The problem is there's none. So it's really case-by-case basis. And here we actually even just talk about one learning rate, where they have a fixed rate. But you could imagine that maybe initially you want to take huge steps. You're pretty energetic. You're ready to take huge steps, get there as close as possible. But you feel like you're getting closer to the target and you start becoming a bit cautious. Maybe your learning rate should decrease. You bit smaller takes at it. So this idea of like having a decreasing learning rate or some schedule over learning rate also becomes pretty much of a norm. And we all do that when training neural networks. And if you really ask me, and I'm pretty sure if you ask anyone, but for sure for me, if you ask me like, why did you choose that particular learning rate? What's the basis for that very schedule? My answer is I don't know. I tried, it worked. So one thing, if you're going to ever venture into neural networks, and just so you don't get demotivated when you start trying, there's a lot of trial and error when it comes to neural networks. There's some derived knowledge from people's experiences, but there's also a good amount which is just about you try it, it worked, and people will publish based on it. So this is why it's important to go off of some people's work, because you don't know, they could have easily taken months to find that very learning rate schedule. So you probably don't want to just ignore it, you probably want to use it. But also know that there was probably no theoretical basis of why that's the good learning rate. He tried, or he or she tried, and it worked. Doesn't mean there doesn't exist a better learning rate. So that's where it becomes fun. Sometimes you can even show that to get a better neural network performance, all it takes is some good initialization and a bit clever learning rate. And there's been a lot of discussion about that as well. Yes?
What do you mean by schedule?
Okay, so schedule means like, for example, I actually, like, so you notice that when I do gradient descent, I do over multiple steps. So I could do something like, I'm going to use this one learning rate, so arbitrary number 10, for first 5 steps. And then I'm going to use learning rate of 5 for the next 5 steps. And then I'm going to use learning rate 2 for the next 5 steps. So this is a schedule of learning rate. Yeah. So now what's going to happen? Now you're all done with the basics of what a neural network is, and you're all very comfortable with this idea. Yes?
So just making a schedule, is it just as good as like online data processing? Like maybe you have a learning rate for some days and you see how much it changed and then you adjust it based on that, or like you have to have a schedule?
Well, so the learning rate is about within one training, right? So you take one neural network, and in training that neural network, you say first n iterations of gradient descent, you do this learning rate, and then next n iteration, you do this another learning rate. I mean, since it's something you basically start and let it train to completion, it's a schedule you want to put in already, right? You don't want to have a human manual intervention step, because despite the fact this sounds tedious and slow process, it's going to happen, like thousands and thousands of iteration happens in front of you very quickly. If you put any human intervention step, that's going to really slow things down. Yeah.
Couldn't you just do it automatic? Just say, whatever that slope is.
Yeah. Yes. So this is something I'm not going to quite cover because it's a bit too much to cover for it to go into it. But when it comes to doing this gradient descent, people have thought about this too. It'd be like, well, this is kind of ridiculous to have to set my own learning rate. Why can't I learn my learning rate, or like be clever about how learning rate works? This is why if you look at in, say, packages like PyTorch we are about to talk about, there are tens and 20s of different optimizers, variations of the gradient descent, and all they really try to do is be clever about how they come up with the learning rate. And to date, there's some that works decently well. There's been back and forth. For example, there's one very famous one called Adam. And don't ask me why it's called Adam. I can answer, but not really. Okay. So Adam is one that's been, people have been really happy about it. Works decently well until recently, or actually a couple of years ago, a paper came and showed actually this original stochastic gradient descent with some basic learning rate could actually completely outperform Adam. And there's another paper came out there, and then you change Adam slightly a bit, and now it performs better. So you can imagine this itself is a huge research topic. A lot of people take a lot of time saying this is how you should optimize. This is a condition under which this learning rate schedule automatically done really gets you to where you want. Oh no, it really depends on case by case. So this is again yet another thing that you just try around to see which one works. I mean, nowadays there are about like 3 or 4 candidates you try and you see which one works. That's kind of how it works. All right, good. Are we kind of clear on the neural network basics? Ready to actually do neural network training? So, again, make sure you go to the repository, pull that from upstream so you get my latest notebooks, and then go ahead, start the notebook. In my case, it's taking. So open up the 0-7 neural networks. Just like all my past notebook, it probably takes some time to open because it's decently heavy. All right. So I made you all install the PyTorch package, and PyTorch is basically one of the leading Python library for defining and training neural networks. So today we get to see it in action and hopefully give you a sense of what you could achieve with PyTorch. One thing I wish I could have done, but in the interest of time not making you do, is first see what it takes to implement your own neural network from scratch, doing everything including forward paths and gradient computation and back propagation. And after you feel like this is too much and you feel like I've been tortured enough, I was going to show how PyTorch is great. But I'm just kind of cutting to the chase and showing the PyTorch is great to begin with, and hopefully you can still appreciate the fact that it's actually saving you a lot of time. All right, so first thing first, as always, we import our essential packages. This should almost become like a second nature to you. Like now, the goal from this workshop is you see a Jupyter notebook and you really have this like itch to just import these packages. If you reach there, it's success. Here we're also going to do Torch or PyTorch. So PyTorch package is actually called Torch. So you import Torch. And there's also a accompanying package I made you install called Torch Vision. And what that gives you is a bunch of data sets that you can train on. And we can actually use one of the data set called MNIST to train on digit classification, and that's provided by Torch Vision. So go ahead and import both of these. This should work fine. I specifically told you in my instructions that this should work fine. Otherwise, you had to come talk to me. All right. Now, PyTorch works on this special kinds of object called tensors. And my succinct summary of tensors is basically a NumPy arrays on steroid. It basically has some additional features on top of NumPy array, but as far as you can probably tell, it's going to really feel like NumPy array. So for example, I can create a new torch tensor, passing in a list of 1, 2, 3, and that just become a tensor with content 1, 2, 3. You can index into it. It has even same properties like shape on it that returns the shape of it. So here's a 1D array of size 3. So it's very, very similar. In fact, even have functions like zeros. So MP0, so remember, that gives you a way to quickly create a new array. You can have very similar function. And there's a tiny difference, but very similar functionality in Torch that gives you, again, another tensor of particular shape filled with zeros. So at this point, you might be wondering, okay, why are we even bothering to learn yet another library that looks identical to something like NumPy? Like, why are we reinventing the wheel? Or why did at least PyTorch guys reinvent the wheel? Well, it turns out they really quite didn't reinvent the wheel because they were trying to show off or anything like that. It's because tensors actually is endowed with ability to work on GPUs. And I'm going to touch on this topic towards the end of this session. But when you actually run your neural network on computers, that's in your laptops, on your CPUs, it's actually quite a bit slow. And you will actually see that this is actually quite slow. And by using GPUs, so for those of you not familiar with GPUs are graphical processing units. It's a very fancy way of saying graphics cards. It's one of those piece of devices that you purchase if you're a heavy gamer and you put it on your desktop. And nowadays I even realize that not too many people even carry a desktop. But if you're a hardcore gamer and you want graphics, good graphics, because that's what games are about, you buy one of these. It could range anywhere from a couple of tens of bucks to upwards of $1,500. You can purchase and throw it in. You can get amazing graphics. You might be wondering, what does this have anything to do with the neural network? It turns out that somewhere along the line, a person came and said, hey, graphics actually have a lot of parallel processing because it's rendering and showing each of those pixels all at the same time. Can I take advantage of this parallel processing? Answer was yes. If you take advantage of this parallel processing, you actually can parallelly process a neural network and get amazing speed up. Nowadays, you cannot really work with a neural network without a graphics card. And I will show you an example. It's not going to really do justice on it because the network we're going to have is very simple. But if you start working with really huge networks, the factor of speed difference can reach upwards of 200. So that's really talking about something that could take a day on GPU versus 200 days on CPU. So you can imagine it makes all the difference. So we'll get back to that again. So when you work on neural network or any machine learning algorithm trying to train something, you need data, right? If you're working on a problem where you have an input and you have an output, you have this like idea of what it should be. This is also called supervised training. You have an answer that you want your neural network to reach. So again, you need a data. So what we're going to do now is use torch vision, and the fact it gives you this functionality to just download data sets. And we're going to get one of the most famous data set to the point like almost every single neural network person, and at least in any neural network course, they're always going to make you at least do something about MNIST. MNIST is basically a data set of bunch of handwritten digits, images of handwritten digits, 28 by 28 pixels, pretty tiny. And the goal is to classify them by saying like what is the digit that's drawn. So it comes with labels as the answers of what is the digit that was drawn in the picture. So let's just go ahead and download it. What you do is you run the next one, Torch Vision Datasets MNIST. This is a function that gives you the data. Here I'm giving a path. So this basically says that get the data and store it here. So I'm basically saying create a local folder called data and run it, store it there. I'm getting a training set. So it's very typical for these data sets to be consisted of two parts at least, training set and test set. The idea is that you get to train your neural network or any algorithm you want on the training set, but to really test whether it's doing good or not, you test it on the test set. It's like if you're studying for an exam, you have a lot of practice questions. But in order to really be tested on whether you got the idea, you don't want to be tested on the practice question. As a student, you probably want to be tested on the practice questions, but as a teacher, you want to test them on completely separate test questions. Same idea here. You train on one data set, and you test on another data set, training set, test set. Okay, so let's go ahead and get the training set. You say train goes true, and you say download is go true because, I don't have it here, so let's just download it. You run it, it's going to take a couple of seconds getting the data. This is where I was like banking. I hope that this is not that slow. Okay, I'm done. So I got the whole data. MNIST consists of total 70,000 images. 60,000 training set, 60,000 training set, 10,000 test sets. So obviously we're not going to spend time just looking through all of them, but let's actually take a bit of a look at it. So first of all, you can look at the length of the training set. Indeed, there are 60,000 images in it. And I can index into a training set. So this returns a particular object that you can index into and returns a pair information, image and label. So if I get the 100th one, index 100, just randomly picked, I can show the image. And this looks like digit 5. Pretty badly drawn one, right? But if you have to guess as a human, you probably would do this correctly. And I'm also putting in title the actual label that came with it. So I know this is actually labeled 5. Okay? And just to give a bit more, get to see the data a bit better, because it's always a good idea to visualize your data. I'm not saying that you have to look at every single 60,000 images, but at least try to take a look at some of them. So I'm taking a look at the first 25 images, and this is what I get. And you can see that there's quite a bit of variations. Just because some people are writing the same digit doesn't mean they all look the same. We know that from experience. And the thing in this particular data set is not too bad, but if you were to really spend some time looking around, there are some really doubtful numbers. Like you really start doubting like what was this person trying to draw, right? So it's not the most trivial data set. It's not like that. You can always obviously tell 5 is a 5. 5 could look like 6. Right? Depends on how a person drew it. Okay, so we got the training set. Let's also get the test set. The only difference here is that you say train equals false to indicate you want the test set this time. You load it. And this time it's pretty quick because when it downloaded, it just didn't download the training set, it downloaded the whole thing. So here when you just say get the test set, it actually is just loading from your local folder. So again, let's look at the test set. There are 10,000 images, as I said. And here I'm just randomly picking one and showing it, and this one is digit 1. So at least this one is pretty straightforward, digit. Okay, so when you work with images, it's actually pretty common for you to want to perform something called data transformations. I'm not really going to step into details, but the idea is basically that you often want to normalize an image. And so what I mean by normalization is that last time when we look at images, we saw that if it's a grayscale image can be minimum of 0 to maximum of 255, or minimum of 0 to maximum of 1, or in fact, just minimum of anything and maximum of anything, right? But as far as human is concerned, when you look at it, and as long as you scale it, it doesn't look like any information was lost. Image looks like image. So what this tells you is that scaling may change your image in terms of values in the array or in tensor quite a bit, but content-wise it may not be that different. But because what you're about to train is a neural network, which is a very much of a numerical thing, if you feed in an image that is 10 times scaled in terms of values, it will get confused. You will not quite understand the fact that image that goes from 0 to 1 is actually the same set of images, say, that goes from now 0 to 255. You will be confused by the fact that this has a dramatically different intensities in pixels. So to kind of help them, and because we don't want to be fooled by something as straightforward and simple to deal with as image intensity and scaling difference, what we do something called image normalization. We basically take whole set of images and compute the mean intensity, so average pixel intensity, subtract that away. Yeah? And you also compute the standard deviation across all the pixels across all the images, and we divide all the pixels by that. Net effect is that as a whole, the image set will have a mean of 0 and standard deviation of 1. So this is called normalization. So this is an image set by image set treatment. This still assumes that within an image set, there's meaningful scale difference. If you loaded one image set and if one image goes from 0 to 255, you expect all the other images to still go from 0 to 255. But when you load another image set and the image now goes from 0 to 1, you expect all the other images in that image set to go from 0 to 1. But effectively speaking, these two image sets should be more or less compatible in the sense that they should be representing something potentially similar. So you don't necessarily want your network to be trained on 0 to 255 to fail on 0 to 1 just because of the scaling difference. So then what you deal with is you take both of these and normalize them. So they both have similar minimum and maximum range as well as standard deviation. So it's a very, very common procedure to perform on images. You normalize the image. Now one more thing is that if you look at the image that was loaded and look at the type, it actually doesn't give you NumPy array as you might expect. It gives you this weird thing called PIL image. This is a package Pillow. There's a package called Pillow. It's an image processing library for Python. It's their image object. It's basically a fancier version of NumPy array. It's a wrapper around NumPy array, in fact, to provide some additional image processing features. And when you load the image from the PyTorch dataset from Torch Vision, by default it returns a Pillow image because you can actually do quite a bit with this. But the thing is, I already told you that PyTorch works on tensors. So in order for PyTorch to understand this image, this has to be put in tensors. Not a NumPy array, in tensors. So basically, before we even get to take the image and show it to our neural network, we have to do two things. Convert it to tensor and normalize them. And that's what exactly we get to do by using Torch Vision's transforms. Torch Vision comes to us with utility function called transform. And what you get to do is create a couple of transformations. So here I'm putting two transformations that's predefined. One is called toTensor. So you can imagine that when something goes through this transformation, it goes in to become a tensor. And next one is normalize. And here I'm passing two values, mean and standard deviation. Here basically what I've done is I've already taken the data set and already computed the mean and standard deviation so that per image you can normalize them, right? So this is something already done for you. I mean, technically it was done for me too because I took this value from somewhere else. But if you were to really meet the brand new image, you do have to spend some time going through a lot of these images and compute the mean and standard deviation. So for the future, you can use it for normalization purpose. But here it's already done for us. We have the mean and standard deviation. So we have these two transforms, and we get to apply these transforms when you load the data. And we do that by passing these transformations into the MNIST loader. But the key is we can only pass in one transform. So since we have two transforms, we have to composite them into one. And that's exactly what this transform so compose does. It takes lists of other transformation, put it into one, and returns one transformation that effectively performs both of these. So long story short, we got an image transformation, so image transform. So this time I'm reloading the train set and test set, but this time passing in transform image transform. Okay, this says that when you load, apply the transformation. Okay, so let's run this. Yes?
Why would that the train is also true?
Oh, that's a mistake. Let's fix that. That's a very good catch. Yeah, please fix that. All right, so training set and test set as such. So now I have a training set. So let's actually just quickly take a look at the training set. And if I load it, and this time if I look at the image, it is successfully returned as a tensor instead of the PIL image. All right, so while we talk all of these things, I'm actually going to hide the thing now since I've shown enough of it. We actually get to finally go to define our neural network. Actually, I skipped this, right? So to define a neural network, what you do is you actually define a new class that becomes the new neural network, and it inherits from this class called nn.module. So typically a neural network implementation looks something like this. You define a class and it inherits from nn.module. Now I'm talking as if you guys know what inheritance is. I haven't covered this topic. So before we actually get to dive into this, we get to learn that. So let's review what a class is again and how actually inheritance works, which is a new piece of information for you guys. So in the past session, we dealt with this idea of like class representing grouping between data and related method functions or methods. Data part becomes the properties and function becomes the methods. And you can think of these as data, property, and behavior. And together they define some nice coherent representation of some concept. It could be, for example, a person. So in the past, we also defined something that looks like this. So class person means this is going to be a person object, or you can create person object. And each person has properties like name. So I have an init that gets called when you create an object. I can pass in the name. So I assign the name to be the name that's passed in. And it has two methods. It has title, which returns some description about a person. So in this case, it's actually a pretty fixed string. It just returns a string, an ordinary person. And it has another method called greeting that uses the information such as the property, the name, and also uses its own other method, the title, to construct the second sentence. So all in all, we define a person. We can instantiate the person. Here I create two persons, or Edgar and John. I pass in the string. Remember, this is going to be the name that gets passed into the init. And now if I call greeting on Edgar, it will correctly use its own property information, so the name Edgar. And same thing goes with John. But they both have the same second sentence because they're using the same title method. Okay, so all in all, these are two classes again, and they have same properties, the name, and they have methods, the title, and greeting. And the key of object-oriented programming is really, again, to combine related data and function or behaviors together to give you properties and methods that you can coherently and keep them together and think about them in some meaningful fashion. It could typically a class, and therefore an object that's out of it, represents some concept. Here it could be representing about a person, but it could be really about more abstract things. And whilst we will see, one of the abstract things, or slightly abstract thing we represent with it is a neural network. Okay, so inheritance. To discuss inheritance, let's actually think about what happens if I now want to define yet another class to represent more specialized kind of an object or class. So maybe I want to represent a scientist. Now, a scientist, after all, is a person, so it probably should have everything a person has. It probably should have a name, probably should have a greeting. But it also has a couple of things specific to scientists. For example, they have a topic that describes what is the topic of their interest, the research topic. And also has a method called research, which you call, it actually performs the research and with a p-value of 0.05 have a positive result. Yeah, so let's actually implement that. So without thinking too much about code duplication, let's just go ahead and implement a class from scratch. Again, scientists should have a name. It will also have a topic. It has a title, it has a greeting. So same thing as what we just saw in the person. It has this new method called research. I made it a bit fancy. I imported above this new package called random, which just gives you ability to generate random numbers. And if you read the code carefully, what I do is I basically say I'm performing a research and I just randomly draw a p-value from 0 to 1. And if p-value is less than 0.05, it exclaims and starts saying it has to publish this. And otherwise, it will continue to try to work on the research. All right, so let's go ahead and instantiate this guy. It's going to be me. I work in computation neuroscience, so my topic is computation neuroscience. So I created myself. Again, I can still greet. I'm a human. I'm a person. I can do research now. So I co-research, and I mean, you know, chances being chance, I don't quite get a positive result. I can run this a couple times until, let's see. Okay, I actually just had one and I totally passed over it. So you can see this actually randomly performs research, and you know, if it gets that particular p-value, runs with it. Yes, this is my cynical joke on the misery behind p-values. If you're ever interested about talking about p-values, what it really means and how you should be actually thinking about it, I'll be more than happy to have a 2-hour discussion of that. You think I'm joking? Actually, some of the people in my lab knows that I do have 2 hours discussions on this. Okay, fine. But the thing is, we have a scientist. It has a lot of code repeated from person. Like this, isn't this like one of those like code duplication that like Edgar hates? Yes, it's a code duplication that I hate. I mean, you should try to be able to derive from the fact this is a person. After all, scientist is a person, right? Well, if that's the case, we get to inherit from a person. We get to say, hey, scientist is actually a special kind of a person. So she have everything a person has and beyond. And you do that by saying, okay, class scientist and parenthesis person. This says that scientist is a person. And notice that there are a couple of things different. First of all, title and greetings are gone. I don't have that anymore. And in my init, I do this really weird thing called super init, whatever this is. I seem to pass in a name. And I also do handle my topic that was passed in. And I still have my research. Okay, so let's just quickly instantiate it. Again, I create a different one called Moku. She's a researcher. She researches physics. And you can actually do greeting. Oh, sorry, actually I'm running on this, the wrong one. My bad. Sorry, this is what happens if I create this at midnight. Okay, so she is a physicist, claims to be an ordinary person, and can we do research? Okay, didn't get a positive result, so maybe not quite there yet. But you notice that despite the fact that now my scientist method doesn't have topic and greeting, it still works. Greeting completely works. This is because inherited those methods from person. So basically, you don't have to redefine it. You just get those methods from free just by being inherited from a person. One new thing is the super thing. This basically says, well, I'm inheriting from my person. In this case, the relationship is said to be the person is a superclass of scientist. Other way to say is the scientist is a subclass of a person. Okay, so, and sometimes these are also referred to as parent-child relationship, but I prefer to do a superclass-subclass relationship. So when you say super, well, it's basically saying, go look up my superclass and look at their implementation of init. That's what super init is saying. Go look up my superclass's implementation of init and use that. And because superclass's init was what actually initializes and sets the property name, you pass in the name, and it will happily set the name property. So this one was pretty straightforward. I could have just said self.name equals name without calling the super init, because super init's really not doing anything fancy. But you could imagine that if the superclass was doing something really complex to get the thing sorted out and initialized, you do want to call it a super init. Okay, so far so good. Yeah.
So you would call super for each one, like super topic equals topic, or is it just for the init?
Just, you could do for other methods as well. So here it's init because I know the init of the superclass does, not that one, so person is a superclass. Person does take a name. That's why I call super init and pass in the name, right? Yeah.
If it took a topic, you would also
You would have also passed in the topic. So if you were to actually have another subclass off of a scientist, then you probably would have called super init and pass in both the name and the topic because that's what a scientist would expect as a init. Then which it would then pass the name information above, but keep the topic and do initialization itself. So it could start to become a bit of chaining if you do a lot of subclassing. Okay, so one other nice thing is the ability to be a bit of specialization by, what was I saying? Is this the one? Okay, this is the one I already showed. Oh yeah, so one nice thing is that you can actually now override an existing method, something you otherwise would have inherited, to slightly change the behavior up. So do you remember the fact that greeting actually uses the method title, right? So what I could actually do in Scientist is I actually can override title. Now I'm providing a new definition of title. Here I'm basically says a title now says a researcher in whatever the topic, but I haven't touched greeting. So notice that I am not touching greeting. Greeting is as inherited, but title is now overridden. Well, what you get with that is if you run this and do greeting, it actually uses the new implementation of the title, despite the fact that greeting itself wasn't modified. So this way of like modifying or overriding some method such that some other method that otherwise would have used that method would change its behavior is a fairly typical pattern. In fact, we'll see this soon in defining our neural network. Okay, so this is like a very quick overview I gave for the inheritance. I hope it wasn't too much. I don't talk about stuff like, maybe if you were to take a purely object-oriented programming classes, they will talk about, on top of inheritance, they think there are 3 pillars of object-oriented programming. Inheritance is one, but there's like polymorphism and encapsulations. I mean, I think inheritance is useful from a practical standpoint. Polymorphism and encapsulations are nice concepts, but you don't really need, at least not definitely here. So hopefully you get a working knowledge, and hopefully that you get the idea that object-oriented programming in this way is really not that difficult. It's just use it as you find necessary, right? All right, so back to the networks. We actually define a neural network module. So this is actually the same module I had in my slides. You're just defining a module, something that takes an input and something takes an input and gives an output. It may have a parameter of its own. In order to define one of those, you inherit from nn.module. It's a class provided to you by PyTorch. This is one of the reasons you're using PyTorch, because nn module comes with a lot of functionalities. It already has a huge amount of properties and methods in it. So by inheriting, you get all of that for free, more or less. But you also get to implement some specific things, because if everyone is just a module, then you don't get to become anything useful and new. So you modify something. Your class is a specialization on top of a module concept, using all the methods and functionality provided by modules, but providing your own so that you can actually implement your own neural network. So here, this is very typical. So what you have to want to do is import 2 sub-packages. Well, one is sub-package and one is yet another sub-package. So one is called NN for neural network. This is a particular sub-package in Torch that you want to use. Module is found inside the NN sub-package. And there's another sub-package even underneath the NN called functional, which basically gives you a lot of functions that you can use to implement the network. Yes?
You don't get functional when you import NN.
You do. You do. You can actually just say NN.functional. But I didn't want to say NN.functional because that's too much typing, so I'm just saying I'm doing aliasing.
So when you just import torch.nn as NN, you don't get functional with that?
You do, you do.
Oh, so you do.
You do, yeah, you totally do. So here you actually do get nn.functional. So everywhere you see f, I could have written out nn.functional. I hate typing,
Oh, I see what you're saying.
so I basically re-import it and rename it as f, so I can just refer to as f. And that's also the convention. Yeah. All right, so I inherit from an nn.module, so now this portion should make sense. nn module is the superclass. My network is a subclass of nn.module. I have my init. And this should also make sense. I'm doing super init. But this time I'm not passing in anything, because module initialization doesn't require any arguments, but it still does a lot of initialization. It has to actually run. So the super init code is a mandatory step. You have to do it, otherwise the whole machinery of module would not get started. So once you're done with that, then you can actually start implementing your own neural network. And here, what you find is that I create this new object called NN linear, passing in some arguments. And it still turns out that NN linear is another module, and it's the one that we actually know. It's the fully connected neural network layer module. So it's something that takes in some number of input neurons, gives out some number of output neurons, and have connection with weights connecting every single pair. That's what a fully connected linear network is. So typically, people will refer to these as either fully connected or simply linear layer. And what they mean by that is fully connected neural network layer. So here I'm having a linear module, and I pass in two numbers, 5 and 10, to indicate this will have 5 input neurons, 10 output neurons. I just create a new module, and I hang on to it by assigning it to a property called FC, standing for fully connected. Yes?
Do you not need to put the FC in the parentheses?
Because the FC is something that's new right now. Init, in the parentheses, you mean here, right?
No, the line above.
The line above.
Sign in itself,
Well, that's because I'm initializing FC just purely based on my internal information. At the time of the creation, I'm not going to ask for any information by the user. So in the previous...
When you're defining scientists,
Yeah. That's because I'm going to ask, when you create a new scientist, I ask you to provide a name. This is a parameter I expect to be passed in. So when you instantiate it, you see that when I instantiate it, I have to pass this in. Because I wanted this information to be passed in, my init needs to accept that information. But in the case of the module, I don't expect anything to be provided by the user at the time of the instantiation. So that's why there's no properties here. There's no parameters here. And I can totally still initialize my property FC just by creating a new linear module. So hopefully that makes sense. All right, so FC standing for fully connected. That's yet another convention. So there goes. Why just define a linear layer? Okay? But you haven't really done anything yet. You really haven't computed anything yet. So temporarily, I'm going to skip the forward, and let's actually just go ahead and instantiate my network. So I instantiate a network. Oops, I actually should have run this. Run the definition. Instantiate the network. Now you get your network object, net. You can even look at it, and it will say, hey, this consists of this one, FC property that is a linear layer. And here it gives even more some basic information, like it has input features of 5, output features of 10, meaning that it has 5 input neurons, 10 output neurons. Okay? Now, what's cool is that if you were to create a torch of correct size, so since it's expecting 5 inputs, if I create a torch vector of size 5 and pass it in, you can actually use my network as if it's a function because it's a module, right? Remember, the module is input to output relationship. So if I create a new instance of a module, I can use it as if it's a function. So I take my network and pass in an x, which I here just created to be a torch tensor. It's a randomly generated torch tensor of size 1 by 5. So it's a vector of size 5. It's a row vector, in fact. I pass it in, and I get y out, which is another vector of size 10. You can actually verify that. It's 1 by 10. And this should make sense because in the definition of my network, the linear network was 5 to 10. It expects 5 inputs, gives you 10 outputs. Okay, so cool, but there's one missing step. Like, how did this computation actually occur? So far, I only talked about init, which initializes the linear module. But nowhere did I use it. I just initialized it. Obviously, that was the method that we skipped over, the forward method. So this is where the PyTorch magic kind of happens. If you call PyTorch like module object as if it's a function, it automatically calls the forward function. So it's kind of we call this something like a syntactic sugar. Basically, you can use it as if it's a function, but behind the scene, it's really just doing the same thing as net.forwardx. That's not 100% true, but good enough. It's really just a shortcut for it. But that's one of the functionality that PyTorch provides you, and there's actually a lot of saving by not having to say net.forward every single time. So, but the truth is, it is just calling the forward function. So when you pass in x, which is tensor, it takes my FC module, which is now a property, right? FC module. FC, again, is a module, meaning that I can call it like a function again. This is what is actually the linear portion of it, the actual fully connected network portion of it. I give vector of size 5. I get vector of size 10 back, because that's how I define the input-output to be for this linear network. And then I use a function element-wise function called ReLU, which is provided under the F, which was again the n dot functional. And what it does is that it performs the ReLU operation we saw, applying that on every element. Now, then finally I get the Z, the final output, and that's what I return. That's all I do here. So together, this actually defines a fully connected linear layer that goes from 5 to 10 with a ReLU activation. This is probably one of the simplest neural network you can implement, but that could actually function. Okay, so I wrote a bunch of other stuff, but I essentially already talked about it. So hopefully this makes sense why we're subclassing what the NN dot module gives, how you actually go about constructing your module out of actually many other modules. Here we use linear module, which is predefined because it's such a typical layer to be used. Another thing you'll find, and I do this sometimes by mistake, listen, like I try not to, but try to be consistent, but layers and modules are mostly interchangeable terms. So when a person talks about a module and then suddenly talks about a layer, they're usually talking about the same thing. So when I say linear module or linear layer, I do mean one and the same thing. Okay. And if you really start to dig into what a layer really could mean, then you start to really encounter like people could have different definitions of it. It's actually a very loosely defined term, such that most times I actually prefer to talk about modules because at least it should be understood that module can consist of many other modules, can consist of many other modules. It's just overall some function. All right, yes?
So the linear, so y equals to self dot f.
Mm-hmm.
Where's the weights?
Good question. So when you created the linear module and told them it's 5 by 10, so 5 input 10, wait, is that what it said? Yeah, 5 input 10 output. In the linear module, because it's a module, it's a function, remember the fact that module is input and output with potential parameters in it, that linear module itself has its own weights. So I mean, I could kind of look at it. That was a bit of a out of scope, but you can say n, and I can look at the FC. That's my linear module. And this has a property called weight, which is 5 by 10 matrix. This is the weight that's going to get trained.
It's random.
Here is random. Yes, exactly. That's another thing. It's by default, it gets randomly initialized. That's a very good point. All right, so finally, in the last 30 minutes or so of the class, what we're going to get to do is train something that's really useful. We're going to get to train a network that classifies the digits we saw. So input is 28 by 28 images, right? But we want this to be fairly straightforward. So one way to deal with this is we actually just take the 28 by 28 image, flatten it out to be 784 long vector, yeah, and then treat that as 784 inputs, input neurons, and just define a fully connected layer on it. Since we want the output to be a 10-digit classification, the output ought to be a vector of size 10. We're going to let it be a probability over different classes. That's what the 10 vector of size 10 is going to represent. And for the sake of mathematical like niceness of computation, we're not going to use probability. We're going to treat it as a log of a probability. If I start getting to y, that's nicer. It gets a bit of longer discussion. So for now, just bear with me and think that the output 10 vector is going to be the log probability. But the important thing being here is that input would be 784 neurons. Output would be 10 neurons. That's just one fully connected layer we can try to achieve this problem by. We'll see how far we get, right? So I define a new module called simple network. Again, inherits from nn.module. Again, you have to do super init to initialize it. And this time I'm defining a fully connected layer to be something that goes from 784 into 10. That's it. Now in the 4, where the actual magic happens in terms of computation, the first thing I do is I take the x, which is going to be the image, and I reshape it. Because currently it's going to come in the form of 28 by 28. Actually, it's going to come in the form of 1 by 28 by 28, minimally speaking. So I want this to be a vector of 784. So I do use something called view. This is similar to reshape, but a bit more efficient. It basically reshapes it into 784. You notice there's a -1 in front. -1 means that just pick a number, whatever, that's necessary to make sure the number of elements still fits. This will become important when we actually start feeding more than one image at a time. If you feed in, say, 10 images at the same time, it will actually look along the line of 10 by 1 by 28 by 28. First number is number of images you're feeding in. Second is the number of channels. This is the grayscale, so there's only one. And then 28 by 28 for 28 by 28 pixels. So you want this to turn it into a matrix where each row is one image. So basically you want to turn this 10 by 1 by 28, 28 into 10 by 784. And the way you achieve that is by saying view it as -1 by 784. You'll pick a number that's necessary to make it fit. In this case, if I feed in 10, it will automatically pick 10, so it will have the correct number of elements. Okay, so long story short, it just flattens the image. So I got a flat image as a vector or a matrix if you have multiple images of it. I feed it into my fully connected layer. Notice that I stopped changing the name of the variable because this happens. I have to have a lot of intermediate values. It's very common for you to just keep on overriding the value of x. So I say I compute the fully connected, that becomes an x. And here I'm doing something even fancier this time. I'm computing something called log softmax. I'm really not going to get into how that works. Essentially what it does is it takes a vector and just normalizes it so you can treat it as a probability. So it makes sure that it's bigger than 0 for sure. Right? Probability cannot be negative. So make sure everything is bigger than 0. And also they all add up to 1. So they properly represent the probability. And on top of it, it actually does a log on top to make a log probability. Again, I'm not going to really get into why are we dealing with this log probability. Just for now, just think that, okay, that somehow stabilizes the computation. We define the network. That's it. We instantiate the network. So every time you instantiate, that's when you get a new copy. Right? Meaning that if I were to get 2 neural networks and basically instantiate twice, I get 2 copies, and each of them could have different weights. It has the same design, but different set of parameters. Okay, so I created the simple network, and look at the test set. This is, okay, test set of size 3. So not size 3. I look at the particular image. It has 30 in it. It has 3 in it. And I can already go ahead and run my network. I can feed my image into the network and see what it says. Right? So I feed it in, I get a vector size 10, but it's like a bunch of negatives and some numbers in it, and it's not quite obvious what this is. This is because this is still log of probability, as I said. So in order for us to get a bit better understanding of what's going on, we have to get rid of the log portion. The way you get rid of the log is by exponentiating this. So we're going to use torch_x for exponentiation to recover the probability. We can verify this as indeed probability by taking sum across all these numbers. Indeed, it adds up to 1. So it is a proper probability over 10 digits. And I mean, you can kind of just appreciate by looking at it. But here, what I get to do is I just pick the index that has the largest probability and let me treat that as the network's guess. So network guess this was 4. It's 3. In fact, label is indeed 3. So it didn't quite get it right. You should be shocked if it gets it right. I mean, by chance you could get it right because, I mean, it's 1 out of 10 chance. But it should not get it right in general because I didn't train this. This is randomly initialized. If your randomly initialized network actually performs well, there's something wrong or at least something weird is going on. Okay, so the fact it's not performing well is completely expected. We have to train this guy. All right, so training neural network, as I said earlier in the slides, we need to define a loss function, something we want to, or cost function that we want to minimize. And we're going to do this by doing gradient descent that uses the gradient over parameters, and we compute that with the backpropagation. Fortunately for you, the whole benefit of using something like PyTorch is that it will perform the backpropagation and therefore gradient computation automatically for you. You don't have to implement that yourself. And it has a lot of functionalities to perform even the gradient descent step for you. So we get to see how that works. So this here is just all me talking about gradient descent and backpropagation in case you decided not to listen to me earlier. Now one thing I didn't quite get into is that when you do the gradient descent, you have a cost function that you're trying to minimize. But the question is, what do you evaluate the cost on? You could actually, for every input, there's a target. Right? So every input image, there's a correct answer, and there's a guess. And you can assess how off you are. But you have thousands and thousands of images. So you could actually think of accumulating the total cost over all the training images and try to minimize that total cost. That would be a total or complete optimization problem. That's good, and you can try to adjust your parameters by validating, say in this case, they have 60,000 images. So we can always run and check what's the total cost across 60,000 images and try to minimize that. But you can imagine running 60,000 images every single iteration of gradient step can actually be pretty computationally prohibitive. It takes quite a bit of time to do that. So rather than actually using the total cost, which requires you to pass through all the training set, you're gonna guess how a network's doing by evaluating the cost on much smaller subset of data. And we call this a mini batch. So typically you take a mini batch of say size 256. So you take random 256 input-output pairs, so input-target pairs, image and the labels, and then evaluate your network's performance on those random 256 sets. And then based on it, compute the gradient and perform a single gradient descent step. And the next round, you take another 256 images and the labels and perform this over and over. And what it can show us that by taking at least random samples, you get a rough view of what the total cost would be. And overall, you can actually do a pretty decent job of optimizing the overall goal of minimizing the cost across all the images. So here, let's actually what you get to do. So the critical thing means that you actually want to be able to look at batches or mini batches of certain size at a time. And PyTorch comes with this functionality called data loader, which actually gives you ability to visit n number of images and labels simultaneously, one at a time. So batches at a time feature. So here I'm basically defining a data loader, which you pass in a data set, and you also pass in a batch size. So here I'm deciding that I'm going to visit 64 images and target labels at a time. So batch size of 64. I pass in the batch size. I'm going to use the same batch size for both. And for the training, I want to make sure I visit them in random order, because if I do in sequence, maybe I'll get biased. Maybe the first batch only consists of zeros and second batch only consists of ones, and that doesn't really give you a good overview of how overall you're performing. So you want to shuffle your training. When it comes to testing, though, we're probably going to use this, but we're just still going to go through the whole test set to evaluate the performance. So we don't really care if the order is shuffled. We're going to actually end up using every single image in the test set to evaluate the performance. All right, so you define that. And you can get a sense of what this does, because the training loader actually isn't iterable, meaning you can visit an element at a time. And an element in the training loader is actually a tuple of inputs and targets. And if you can actually look at it, the inputs and targets here are actually tensors. Inputs, the x, the images, will be 64 by 1 by 28 by 28. This means there's 64 images of one channel, so grayscale 28 by 28 pixel images. That's your digits. And another one is simple vector of 64. These are 64 labels. So it would just give you 0, 1, 5, 7, something like that for each of those corresponding points. And it visits 64 at a time, because I specified batch size to be 64. Okay, so now armed with this, we can iterate through this. Yes?
So after you look at this 64, does it throw it away then with that?
So okay, so the question is like, does a sample with replacement or sample without replacement? Right? Correct answer is it does by default sample without replacement, meaning that if it looks at this 64, it puts it aside and looks at next 64. And in fact, this iteration has an end. It basically keeps on doing it. As soon as it runs out of it, the iteration stops. Right? And we'll actually take advantage of that fact. All right, so we get to finally start to think about training. So again, we instantiate a network from scratch. We do this thing called .train to say, okay, I'm about to train a network. I'm not really going to step into what this really does. Just think that every time you're about to train, you have to tell the network that you're about to get trained. And here I'm actually iterating through my training loader, meaning I'm visiting 64 at a time. I wrap it with enumerate. I hope you remember enumerate. That just gives you count on which particular position you're in. So how many batches have you gone through is what the enumerate is going to give you. So that's the first one. Since the actual element is a pair of information, I'm also unboxing it or expanding it into data and target. And all in all, but per iteration, I feed in these 64 sets of images into the network. I get 64 sets of outputs from the network. And I compute the loss. Now, loss we're going to use is something called negative log likelihood loss. It's not the squared error loss. It's basic. I'm not going to get into this again in the interest of time, but you can essentially think that this loss will be minimum if the target class has the highest probability among all the choices. In fact, it would be the minimum if the target class is 1. Basically, if you say at the end of the day the probability of that particular target class is 1 and everything else is 0, if you say that that's the best case, and your score will be your loss will be very, very low. And otherwise, if you have a mixed answer, your loss starts to become bigger. That's what the negative log likelihood actually computes. Okay, so that's what we're going to try to minimize. So we could run this, but notice this is not really going to train anything. Now, if you run it, it's going to actually run for a couple of seconds. Yes, what's up?
So the output is 10 vector, right? Vector 10 elements.
So output in this case, since I'm feeding in 64 images, would be 64 by 10.
64 by 10. So that NLM score loss already does the max on those 10 to find the max value. It already does those computations.
It does computation across those 10 numbers to figure out. It doesn't actually do a max. It actually looks up what's the assigned probability on the actual correct class and determine how well you're doing. Because it knows the best cases has to be 1 there. Okay, so what we're missing here is still 2 things: backpropagation and gradient descent step. Right? It turns out you can actually do backpropagation just by taking loss and calling backward on it. So if I say a loss and say dot backward, that's it. That actually performs all the backpropagation and computes all the gradients out there. But now you still have to do gradient descent step. The gradient descent step is something you perform using an optimizer. So optimizer is something you can actually import from. So actually, did I import the optimizer? No, I actually just use Torch Optim. So optimizer is something you can actually find on the sub package called Optim, and there are a couple of choices in it. So this idea of doing mini batch gradient descent, where you sample random mini batch and do gradient descent and do the next sample of mini batch, this has actually a fancy name to it. It's called stochastic gradient descent. It's stochastic because you're randomly sampling. So this is the most basic gradient descent you can perform, stochastic gradient descent. And we're going to go ahead and just do that. There are, as I said, there are other fancier ones like atoms and autographs and stuff like that. We're not going to really explore here. We're going to stick to the basic. We create a new optimizer, the stochastic gradient descent optimizer, and you pass in net.parameters. What that does, if you call net.parameters, what it does is it returns a list of all the parameters in your network. Since in our case there's only one linear network inside, it essentially just returns that weight. But if it was consisted of multiple layers, the parameters would return lists of all the parameters. And I'm not going to quite show you. You can explore on your own to see what it consists of. So you're basically saying, I'm going to optimize over all these parameters. And notice that you pass in LR, which is the learning rate. This is how the multiplier in terms of how big the step should be, something we already discussed. Okay, so you finally get an optimizer. At the beginning of each iteration, you want to make sure that all the gradients are initialized out. As in, like, any gradients you computed from the previous step doesn't remain around. If it does, then you can start getting wrong answers for the gradients. So you have to zero the gradients out. So you're about to compute new sets of gradients. You do the feed forward pass. You pass in the data, you get that output. Remember, that's a feed forward portion of it. You compute the loss. So that's the final loss function, loss output you get. Now from starting there, you perform back propagation, which asks the question, how does the loss relate to every one of my parameters? That's what the backward does. Finally, by calling optimizer.step, optimizer knows how to take all those gradients computed and applies them by performing and modify the parameters according to gradient descent using the learning rate. That's it. So a lot of things are obviously happening behind the scenes, but we can just appreciate the fact they thanks to the developers and just use it. So run it. Okay, so it's running. It's done. Cool, it's done. Problem is, like, we forgot one thing. We forgot to put some monitoring on it, right? Because otherwise, I would not be able to tell whether this is actually running or it's getting stuck somewhere. Is it even training? So often, what you want to do is you want to monitor the progress of your training. And you do so by adding something like reports. So every once in a while, you print out what's the current loss. How well are you doing right now? If everything is going well, loss should decrease over time, over iterations of the gradient descent. So here I basically put an if statement saying if batch index divided by 100 is equal to 0. That's another way of saying every 100 iterations. Yeah. Then I print the loss. And also notice I imported this module called time, which provides time.time function, which gives you the current time in seconds since the beginning of whenever the computer world. I'm actually not that joking about that, but it gives you some number of seconds from some set time in some past. All you care is you're going to keep track of that. You wait and then you recompute it and take the difference from the beginning. That gives you how long has it been since you just started till now. So basically duration of the training in seconds. So with that, let's run it. Now you get a bit more interesting outputs. You can see the loss starts out pretty high, 2.37, but after just 100 iteration, it immediately drops to 0.59. And then after a while, it still continues to go, but it seems to be somewhat stalling around 0.31. Okay, so loss decreased for sure from the beginning. You took 5.11 seconds to run. What you just ran is one whole run through the data set. Because the iterator goes through 64 images at a time through the whole data set, once it exhausts the data set, it's done. Okay? All right, so cool, we just trained our neural network. Now it's time for to find out how good is our neural network. So the way you do that is by put your network in evaluation mode. You're not training anymore, you're evaluating the network. And here I'm not going to really step into the details. I have a pretty heavy commenting on it. Basically what I'm doing is just stepping through my test set now and compute the cost over every elements of the test set, sum it over, and then divide it by the number. So that becomes my average loss. But more importantly, I also compute the argmax, meaning the best guess of your network per image, to see if you get it right or wrong, this 0-1 answer. And I count number of times it gets the image correctly. All right, so I can run it. And this is what I get. I basically get 91% accuracy. So you already, with this simple network, train something that can classify your digits up to 91% correct. So you can kind of try, and this is going to be hit or miss. Let's see. I take the same image as before. I think the answer was 3. Let's run it through our network and see if it gives me the right answer. Indeed, it gives me the right answer. So you got a network at least gets this example correct. And in general, gets 91% of the digit classification done correctly. Okay, so that's already something. The chance performance here would have been 10% if you're randomly guessing. So it's far better than chance performance. And all you did was one layer. Remember I said that you can actually stack these up to get far more complicated one? Why not try that, right? So let's actually, instead of doing single fully connected, now go for 3-layer fully connected. So here I'm putting 3 layers in. So now in my complex network, so-called, has 3 linear layers. The first one goes from 784, again because it's a flat input of image, to some arbitrary choice of numbers. I just decided 200 sounds cool, so I said goes to 200 intermediate hidden layer neurons. That 200 hidden layer neurons then goes to yet another connection, fully connected layer for another set of 200 hidden layer neurons. So this has 2 hidden layers. And then finally, obviously, the output has to be 10-digit classification. So I go from 200 to 10. I have 3 linear layers. And again, I do a couple of tricks. I flatten the input so that 28 by 28 becomes a 784 vector. I feed it in. I wrap it with ReLU because I want the activation function, right? I do it here for between the first layer and the second layer, and then the second layer and third layer. But I don't do it at the output because my output just ought to be whatever it wants. There's no reason for me to want it to clip it at positive numbers. So I don't put an activation at the output. This is just a design choice. I'm not telling you can never do it. I just decided this is how I'm going to do it. And again, I want to make sure this is a proper probability. So I put through the log softmax to get the log of a probability. And finally, that's my output. That's all. So now I've actually successfully defined 3 fully connected layer neural network. Yes?
I think I missed this. What determines the number of layers that you want to?
Nothing. Your heart.
It's your heart.
Yeah. You simply go based on what you want. I mean, I could have gone for 5, I could have gone for 10, I could have gone for 30. You will find a point where you're really not training well. The more network layers you have, the more difficult it actually becomes to train. It becomes more like care given to the exact learning rate and schedules to even get it going in terms of training. But theoretically speaking, you could squeeze out better performance out of it, right? So yeah, this has been where so in general, if you look at the field over the past 6 years, which is really how long this field has been around, for the neural network being the real thing nowadays, over the past 6 years, it's been getting deeper. So like the very first one that classifies like very complex set of images in the Haskell ImageNet, it was about 8 layers. Now one of the deepest is about 400 layers. Probably deeper exists. 400, I don't know if it performed the best, but you can go deep. You can go pretty deep, and you tend to get more performance out of it. But time and time, people come around and say they actually can show that they can actually achieve some amazing performance with not that many layers as well. So more layer doesn't guarantee better performance, but it does give you more complicated function that could potentially get you that extra performance out of your network. Yes?
Also, I was wondering how to choose to call activation function.
Mm-hmm.
So the Virgo here, I remember some use like sigmoid function.
That's correct. So sigmoid is old. Long-lived sigmoid. Well, that's actually dead. So sigmoid is dead. There's been many arguments as to why sigmoid is not that good. Sigmoid basically has a flat section that makes gradient very terrible. It has hard time learning. There are many arguments about it. So short answer to your S1 is, again, your heart. You basically go based on what people have tried, what you tried, what do you think works. Hopefully you're getting the sense that there's actually not a lot of prescription when it comes to neural networks. You kind of just try stuff around. There are things that people tried and show that it kind of works. You go off a bit, but you change it. That's how this field is. It's pretty fresh field. It's 6 years old, really. All right, so to the point that basically today what I'm telling in terms of all this thing with the ReLU, probably in a couple of years, is completely irrelevant. Well, to the point actually this network is also considered this is classic, right? Today's cutting edge wouldn't look quite like that. There's a lot of fancy features that people throw in to get the extra performance out of it. All right, with enough of that, let's actually just go and train our tree, this flashy tree layer network. Same exact thing, nothing really different, and I'm just training it. Okay, it took 5.88 seconds to go through all the data set. Now, hopefully you notice that, one, it's a tad bit slower. But more importantly, it seems to be still decreasing in the performance. But I kind of finished already. This is because I only got to go through the data set once. So one whole pass-through data set is referred to as one epoch. And if you actually train a fairly complicated network, so even tree-layer networks starting to really get complicated enough, you actually want to go through multiple epochs through your data set. So you want to go through multiple times. So we actually let that happen by having yet another for loop outside that repeats this traversing through train loaders. Here I'm going to visit it 5 times. This is 5 epoch training. And notice I also changed my message to indicate which epoch you're on, so you don't lose your mind thinking you're still on the 0th epoch forever. So I'll let it run. This time it's still continuing. It's done with the 0th epoch. Now moving on to the epoch 1. You can see that this is kind of the norm of a neural network trainer. You basically sit in front of your computer and stare at the numbers decreasing potentially. Okay, so it's working. It's hard. It's really working hard. See, you're actually getting pretty decent performance. It's already reaching like 0.19-ish. 0.14 now, 0.07. Okay, so overall, it took longer because I went through 5 times as much data. But the cost seems to have gone down quite a bit. Okay, let's test it, right? So now evaluation, test it on the test set. You don't have to go through multiple epochs through test set. The whole point is to see on the test set how well you think performs. Let's run it. And 93%. So earlier it was like what, 90%? 91? Okay, 2% improvement. Hooray, we got some improvement over it. So yeah, this is how you actually get more complicated network to train and get a bit better improvement over it. So this is the end of this notebook. I have another notebook just to showcase how you can actually go about more complicated networks and how you can actually run it without losing your mind. Okay? So here, actually let me just show it there. Here, I actually provided, so you can actually open up this 07EX, more complex network example. This is an example of notebook in which I have content already all run for you. The reason being, if you try to run this on your own, it's going to take minutes to run at least. And also part of it's going to run on GPU, which you probably don't have on your computer. So let's just take a look at it. So here the first one is just importing all the packages. The dataset loading is exactly the same as we did in the previous one. The key is the network. Now I have come out with a different network and has more complicated structure. I even used some new module called convolution, which I haven't even talked about, and I'm not going to quite talk about it this time. Whole key point is that this uses a bunch more new features. It makes it more complex. And as a result, much more complex to even run it. It would take longer to just run and let alone train this network. So if you were to take this network, instantiate it, yeah, let me actually just do at least part of this. Don't try to follow it because you will get your computer stuck training this for a couple of minutes. At least I can show you in a sense what it feels like. So here I already ran it for you. You can see the whole thing takes 154 seconds to run. And by the end of it, if you're tested, this achieved 98% performance. So this performs pretty well. I mean, just to give you a sense of how it feels like when you train this guy. Okay, you get a sense of it, right? So it's pretty slow, right? It's very slow because it's working hard on CPU. Now, it's said that if you actually try to train any of the current modern day networks on a CPU, I mean, I told you earlier that the factor of difference could be anywhere as 100 to 200 as compared to running things on something like GPUs, which can massively parallelize. So to give you a sense and appreciation of what GPU could do to you, so that maybe in your next birthday, what you're going to demand is a GPU, I'm going to show you what it looks like training on a GPU. So the way I'm doing that is I'm actually connected to my lab computer that houses quite a few GPUs in it. So what I do is I instantiate my network, and I do this thing called to CUDA. This is the same thing as saying push it to GPU. I put my network onto GPU memory, and I also put all the data sets onto GPU memory so everything can happen on GPU and take advantage of its massive parallelization. So here, if I just run this thing, no, so CUDA is the name of the computation set. It's basically so CUDA refers to NVIDIA GPU Special Computation Library. So it's said to be similar. So you can see this runs much faster, right? I mean, it's still not like immediately finishes, but at least you don't have to sit and there's enough progress getting made. So I will let this finish. I think it takes about a minute to finish the whole thing. You don't have a GPU. If you're running on a laptop, I can almost guarantee you don't have a GPU. Nowadays, no laptop comes with a GPU, should come with a GPU. It makes no sense for you to have a GPU on your laptop, unless you're a gamer. Yeah, I gave you that unless the gamer cost. Okay, did it? Okay, all right, so it's finished. So this time it took 50 seconds. I know I lost the thing, but if you were to have to try to complete this, it would have taken about 160 seconds-ish. So you get factor of 3 to 4 improvement. You're saying what happened to the factor of 100 improvement? Well, you don't get as much improvement here because despite these changes in the network, this is still considered a very simple network. If it's too simple, you don't actually get that much of a benefit out of the GPU. But if you start doing any of the things like what people are trying at the cutting edge, GPU is a must. Otherwise, something that could take a day on GPU would literally take months on CPU. You're not going to be able to compete at all. By the time you finish training that network you're training is completely outdated. That's how fast this field moves as well. All right, finally, we can just quickly evaluate it. And this one, I mean, we know it gets about 98% performance. So obviously, performance difference wouldn't come just because I'm getting the GPU. What you get is performance time decrease. All right, so that's actually a pretty good ending point. That's all I have actually for today as far as the neural network is concerned. It was pretty, rushed visitation of all the material I wanted to cover as for neural networks. But at least I'm confident to say now you've been exposed to neural networks. You at least hopefully get an idea of what module is, how networks are nothing but just the connection of modules, how if you have a module you can actually do forward pass, And if you can do gradient with respect to the input and gradient with respect to parameter, you can just do backpropagation to get the gradient, and you have an idea of what a gradient descent is to do optimization. And PyTorch is a library, one of many libraries, but one of the leading Python libraries that lets you build and train neural networks, where it gives you things like backpropagation and gradient descent pretty much out of the box for free, so you don't have to implement them on your own. All right, I know this is like a very hot topic, and people like this topic in general. And like as I said, 2 hours is not going to really be able to cut in terms of showing everything I like to show. There are many, many other topics that could be discussed about neural networks, but hopefully you get a taste of it. If you've never been exposed to it, hopefully you now understand that this is actually not that difficult. All right, so with that, any questions? Good. So that's all I have for today. The next session is the last one. I'm going to cover something like data organization and a bit about package installations and management stuff on Python, and a bit of wrap-up discussion and like additional learning resources as a topic. All right, cool. That's it.